So in our last video we talked about the Fundamental Theorem of Calculus Part 1. This time we're going to talk about the Fundamental Theorem of Calculus Part 2. So we are going to consider that we have a function, it can be anything really, for any x values really in its domain, bigger than 0. The big F of x is then the area determined by the graph of the curve over the interval from 0 to x, as an example is shown here in the graph. We can use the Fundamental Theorem of Calculus Part 1 along with the fact that the function is an antiderivative of the other function. We can find a particular solution for big F. Since big F is equal to 1/3 x cubed in this case, or x cubed over 3, we can see the derivative of it is x squared. We've seen when given big F is the indefinite integral from f of t with respect to t. F of t has always been the derivative of big F. However, this is not always exactly the case. We're going to use this part 2 of the Fundamental Theorem of Calculus to discover a rule for when it will or when it will not be the derivative of f. And how we can find that derivative if it is not, we can consider 3 cases, which we'll look at in our next example. We want to discover a rule for evaluating expressions. In other words, why can't we say that the result is always going to be the derivative of the integral is going to be the function? So here in our next example, example 3, if we were using our note packet, we find the derivative of the function in 2 different ways. First, we're going to use the Fundamental Theorem of Calculus Part 1 to find just f, and then compute f prime. And then we're going to use the Fundamental Theorem of Calculus Part 2 and compare our results. So with case 1, we know f of x, big F, is equal to the integral from pi to x of cosine t dt. Now, I know when I take the integral of cosine t, I get sine t. So big F is going to equal sine of t from pi to x, which means we're going to take sine of x minus sine of pi, using that first part. Sine of x is just sine of x. Sine of pi, on the other hand, is 0. So we're going to end up with just the sine of x. From there, if I find the derivative of that, we're going to end up with just cosine of x. So in this case, we do get the function back. They are inverses. So cosine x is the derivative of big F. Now here in case 2, I know that the square root of 1 plus t can be written as 1 plus t in parentheses to the 1/2. I don't have to always write it at this point. I just know that that's the case. So when I'm trying to find big F, I take 1 plus t and I increase the power by 1. So the power is now going to be 3/2. And we multiply by the reciprocal of that, which is 2/3. And we're looking at that from 0 to x minus 3. So now let's keep evaluating. We're going to have 2/3 times 1 plus x minus 3 to the 3/2. Minus, if I put 0 in, I'm going to end up with just 1 to the 3/2. Now, let's simplify everything. We're going to have 2/3 times x minus 2 to the 3/2 power minus 1. Pretty reasonable. Now, if we were to take the derivative of that, what we're going to end up with is just the square root of x minus 2, which in that case is not giving us what we started with. So this one did not work. To say that we have, when taking the derivative of the integral, we get the function back. So now let's look at case 3 here. We've got t squared from 4 pi to cosine x with respect to t. So I'm going to take big F. That's going to equal t cubed over 3 from 4 pi to cosine x, which means I'm going to have 1/3 times cosine squared x minus 4 pi cubed over 3. Okay, so in this case, when I take then the derivative of this, I bring down, and actually this cosine should be cubed. I bring down the 3, which will cancel out the 1/3, and I'm going to have cosine squared x, but then through the chain rule, I have to take the derivative of just the cosine, which is negative sine x, which gives me a final derivative of negative cosine squared x sine x, or you could also say negative sine x cosine squared x. Either way is fine. Which again does not give us t squared back. So now in example 4, we want to see if we can predict what's going to happen to the derivative of big F when the antiderivative is not a named function, as in this particular case. So we are going to be looking, well, we know from our last lesson, e to the x, the integral of that is just e to the x. So we're going to end up with, in this case, e to the x squared times 2x, which is e to the x to the 4th, or let me clean it up a bit, 2x e to the x to the 4th, which is not e to the t squared. So what we can say for the Fundamental Theorem of Calculus Part 2, if big F of x is equal to the integral from 0 to g of x of f of t with respect to t, then the derivative of f is going to be f of g of x times g prime of x using the chain rule for derivatives. So now let's look at some examples, some more examples. So example 5, if the derivative of f is e to the negative x squared and f of 1 equals 3, we want to find f of 2 using a calculator. So I'm going to just write some stuff down first and tell you what I get when I type things into my calculator. So when I'm finding, or what we need to do is find the integral of e to to the negative x squared with respect to x, using the fundamental theorem of calculus, that would equal, if we are going from 1 to 2, equal f of 2 minus f of 1. Now, if I'm doing all of that, I'm going to put what I need to into my calculator. I'm going to get, for this integral portion, 0.13525 equals f of 2 minus 3. Now, I kind of got that decimal portion by putting a 1 into the x. Correction, I got that decimal deal by putting 2 in for x and 1 in for x and subtracting them. So now I'm going to add 3 to both sides and find that f of 2 is equal to 3.13525. So now let's check out our last example. So example 6, we're going to let f of x be a function whose graph is shown below, and we're going to use the graph of f and the fundamental theorem of calculus to answer the following questions about big F. So first, to fill in the table, what we're going to do is we're going to find the area from 0 to the given x value. So when x is 0, the area under the curve is going to just be 0 because we're at the origin still. Now when I am moving along to find the rest of these, I look at 1, I've got a triangle there. If I find the area under that curve, I can find the area of the triangle. Remember, area of a triangle, base times height divided by 2. 1 times 2 divided by 2 is 1. So at x equals 1, f of x will be 1. Now I can expand this to this 2, and I've got a trapezoid. The area of a trapezoid is to add the two bases, multiply the height, and divide by 2. So 1 plus 2 is 3, times 2 is 6, divided by 2 is 3. And we're just going to do this, keep moving along through the picture. Now at 3 I've got another trapezoid. Base 1 is 1, base 2 is 3, 1 plus 3 is 4, times the height is 2, so 8, divided by 2 is 4. Okay, we keep going. Now I have that trapezoid, which we know the big trapezoid is 4. The area of it is 4. And now I have this little triangle here to add. So that's going to be an area of 1, but it's below the curve, so we have to subtract it from the previous one. So we're going to get 3. And now we find the area of that big triangle. Again, it's 2 of the same little triangle, so we just multiply the 1 we got by 2, and we're going to get that big triangle has an area of 2. If we add that to the 4, but since the 2 is below the curve, we actually are subtracting. At 5, big F is going to equal 2. So we can then plot the points in our table to complete the graph of F. And I'm going to do that. First, I'm going to erase the colors I made on the graph. And then I'm going to do all of this in a red pen. So I have a point at 0, 0, at 1, 1, at 2, 3, at 3, 4, 4, 3, and 5, 2. So that means we can now connect them, and we've got the start to our graph of big F. Now, for part C, where is the 0 of big F? Well, that 0 is at the origin, at 0, 0. And the total net change in F, if we take F5, F of 5, and subtract F of 0, we're going to get 2 minus 0, which means we're going to have a total net change of 2. Now, how does the total change of f of x compare to the net area bounded by the graph of the function? Well, guess what? They are the same. So the maximum value for our big F, we found, that is 4, and that occurs when x is equal to 3. And that wraps up our lesson on the fundamental theorem of calculus.